This is V naught and V naught changes. Okay. So, let us say VICM is fixed and V naught changes. How will it change? Obviously, it is because some differential voltage has been applied in some way. But like I said, the differential voltage applied itself is so small that we ignore that, but it is not that the output will change without the input ever changing. Okay. So, the input will change, but by a small amount. Okay. So, now, so let us say V naught becomes very small. Okay, because a negative, if you apply a negative VD, V naught will fall. If you apply a positive VD, V naught will rise. So, let us say you applied a small negative VD and V naught keeps falling. Okay. At what point will any transistor get out of the desired M2? Okay. So, again this gate voltage is rising because VD is positive. Okay. There is always a possibility that M1 goes into triode region, but that is what I was saying earlier. This VD is so small that we do not consider those possibilities, we do not have to worry about those things. Okay. The big change in voltage is only in the output voltage. So, what happens as the output becomes smaller and smaller, the gate voltage of this is nearly fixed, again VD is very small, right. So, the gate is fixed at VICM of M2 and the drain keeps falling. How far can it fall? How far below the gate can it fall? Huh? It should be greater than VICM. What should it be? Minus VICM minus VT. So, the drain can go below the gate, but not by too much, not by more than one threshold voltage. Okay. The condition for saturation is VDS greater than VGS minus VT, or many times easier one to use is VD greater than VG minus VT. I get this simply by expanding VDS as VD minus VS and VGS as VG minus VS, that is all. So, in this case, ignoring any small variations in VD, VO has to be greater than how much? VICM minus VTN. Okay. So, the output swing limit also depends on the choice of the input common mode voltage in this particular case, in this op amp. Okay. So, this is important and sometimes the two can be linked, sometimes one of them will limit the output voltage, sometimes it is some combination of the two. Okay. And let us say because of applying a positive VD, V naught keeps rising, then what happens? Which transistor gets into trouble? M4, right, very clearly, because this is fixed, this is rising. So, this voltage across M4 is getting smaller and smaller and M4 is getting squeezed. Okay. So, what is the upper limit on V naught? What is the upper limit? What is the minimum voltage you need across M4? VSG minus VT. How much is that? VSG3 minus VTP. Okay. How much is that? Square root of I naught by KP3. I will use the symbol 3 for both M3 and M4 and 1 for both M1 and M2. Okay. So, this is less than VDD minus square root I naught by KP3. Okay. This is fine. In fact, you would like the swing limits to be as large as possible, right, because you have a certain supply voltage and you would like to use all of the supply voltage for the signal, as much of it as possible. Okay. But always there will be some limit, I mean you can't go all the way to the upper supply, that is in any, usually in any circuit, especially circuits that do not use inductors, the output voltages in electronic circuits will be confined to the supply rails between 0 and VDD. Okay. So, one of the things is to try to make them go as close to VDD and 0 as possible, but you will never be able to go all the way to VDD or all the way down to 0. This is because always you will have some component, some transistor between the output and VDD, right. and you have to have enough voltage across that device. The best thing you can do is have just one transistor between the output and the rail. Okay. So, in fact, here between the output and the upper rail there is just one transistor, you have to leave room for just one transistor. So, it is optimum on the upper side, but on the lower side you have two of them. So, this does not go very close to ground at all, but it goes quite close to VDD. You had some question? Yeah, so you tell me, will any transistor cut off? Actually, the way I have set up the circuit now, there is no load, right. So, what is the current in all the devices? I0 by 2. So, the current is not changing at all. The incremental currents in all the devices are very small. Okay. So, if I had connected an external load, that is a good question. I mean, before I went on about saturation and cutoff, but now I did not worry about it. The reason is because I do not have an external load, the incremental currents are very, very small. Okay. They are not 0 because the gain is finite, there will be some small incremental currents flowing in the GDSs. Okay. So, but that is all that we have. So, the incremental currents are so small that none of the transistors will cut off in this particular situation. Okay. Yeah, that is correct. So, that is the reason why in that case we do not, I mean that is correct very much. I mean, if you have multi-stage op amp, it is the input common mode swing of this that is relevant. The output swing is not relevant because it is not going to swing much. It is the output of that stage that will limit. That is correct. So, it becomes even less critical. Any other questions? So, now if you make a circuit using this op amp, first of all, in any circuit, even without knowing all of this, you can go and evaluate the swing limits from scratch, right. You can evaluate the incremental voltages, total VGS, VDS and ID of every device and find out when any device goes into saturation or cutoff. But again, as we make more and more complicated circuits, we have to make macro models for a collection of transistors. Otherwise, I mean, it becomes too painful, right. You do not go into the transistor level for let us say 1000 transistor circuit, you will build it up hierarchically. So, for an op amp we have some swing limits. Okay. So, now we have the swing limits on the input common mode voltage and the total output voltage. Okay. And this we can use to calculate the swing limit of any other circuit we make with it. Okay. Let us take the example that we took earlier. This is a unity gain buffer made using this op amp. Okay. I will call the input bias Vi0 in order to not confuse notation. In the operating point, what will be the output? It will be Vi0, right. Okay. So, now what is the input common mode voltage of the op amp? The input common mode voltage by definition is the average value of the input voltages. What is it? It is Vi0. Okay. Now, we know that we have a supply voltage from 0 to VDD and VICM is limited to some values. Okay. So, there is some limited range over which VICM can vary, that we have calculated, right. VICM has to be in this region where the upper limit is VDD minus VTP square root I0 by Kp3 plus Vtn. Okay. And this lower limit is Vtn plus square root I0 by Kn1 plus square root 2 I0 by Kn0. Okay. So, first of all, when you design an op amp circuit, you design a circuit like this, you have to choose Vi0 somewhere here, isn't it? Obviously, otherwise it will not even work. Is this correct? So, we assume that output will follow the input. All this is true when all the transistors have high gain and everything is in saturation and so on. So, first is you to choose the value of Vi0, you have to look at the input common mode limit. Okay. and the output also has some limits. So, it depends on the chosen input common mode voltage. So, VO will vary between these, where this is VDD minus square root I naught by Kp 3. Okay. Now, in this particular case, so you have to look at this for again now we apply a signal. So, Vi 0 plus Vi, what will be the output? Approximately the same. Okay, let us ignore that Gm by Gm plus GDS, that number. So, this is approximately Vi. Okay. So, what are the conditions you have to satisfy? Yeah. So, now what is the input common mode voltage when the input is applied, when the signal is applied? What is the common mode input of the op amp when the signal is applied? No, the total common mode voltage, what is it? It is just the average of these two, right? It is Vi 0 plus Vi. Okay. So, if you have a non-inverting amplifier, this is always the case. And then what is the output voltage? That is also Vi 0 plus Vi, the total output voltage. So, you have to make sure that both of these have to be in the respective limits. Okay. Then you choose Vi 0. So, one of the goals usually is to maximize the amplitude of the lowercase Vi, the input signal that you apply. So, you have to choose Vi 0 such that you can apply the maximum value. Okay. So, that is the philosophy. I did not take the numbers, but once you, if you have the numbers for all these transistors, you can calculate and find that out.